Okay, everybody's here. Great. Okay, we continue with the transforms in the frequency domain or the Fourier domain. And there are some other concepts that we have to talk about. We use these concepts in their place, but first of all we should know about the theory, and then we can explain how we can leverage all of these concepts in some practical experiment. So let's have a very quick review of what we said about the transforms. So the discrete time Fourier transform. Discrete time Fourier transform is the representation of the signal in the Fourier or frequency domain using the eigenfunctions of e to the power of j omega n. And we saw that the analysis for this comes as a series like this, but the result is a function which is periodic because of e to the power of j omega, and also continuous with frequency because omega is a continuous frequency. And this synthesis form, which is normally not used, we normally use the definitions to get the synthesis form of that. So we talked about the properties of the Fourier transform, how can we get the Fourier transform for a kind of signal, and we saw that if the signal is absolutely summable, which means that it's convergible, then we have two properties, and the result of these two properties comes up with the idea of having the frequency or the Fourier transform for a signal or not. If it's absolutely summable, then the Fourier transform definitely exists for each frequency, and also it's continuous with the frequency. So with respect to the frequency domain, that would have a continuous form. And we got this result that if it's not continuous in the frequency domain, if it's not continuous with respect to the omega as the horizontal axis, then it means that it's not absolutely summable. And we saw that absolutely summability is another meaning for stability in the concept of Bibo stability. So Bibo means bounded input, bounded output stability. There are different types of stabilities, but in DSP, when we talk about stability, we normally mean Bibo stability. So a bounded input should give us a bounded output. That's the meaning of stability in DSP. And here, the absolutely summability, it means Bibo stability. So the signal is stable if it's continuous with the frequency and the other way around. And if it's not continuous with the frequency, as an example I showed the ideal low-pass filter, which is not actually continuous in the frequency, so we have this continuity here and here, for example, in the cutoff frequency and the initial frequency. It means it's not stable. When it's not stable, you're not implementing that. You're not able to implement that. What you do is just approximating this ideal filter. And the result of approximation comes with these fluctuations or the overshoots, which are called Gibbs phenomena. So Gibbs was the first person that understood this kind of phenomena. Then we talked about, so these are the consequences of the DTFT theory for different signals, and then we talked about the ideal window, and we said that when the stream of data is coming, you're not able to take the whole data and then start to show the frequency components. So what you have to do is practically you have to put a window on part of the signal which is called framing or windowing, and then you will get the signal in that part. But when you go through the frequency domain, you should know the result of this kind of activity, what it actually brings up. The point is that windowing by itself somehow corrupts the signal. And the corruption comes from this point that windowing in the time domain is corresponding to the sink in the frequency domain. And we know that in the frequency domain, the DTFT is periodic. So this sink function will be periodically repeating. And we know that this sink function in the edges, in the final ends, in the limits, is not actually zero, such that periodicity of this block, of this sample or the pattern, so makes problem. You're not starting from the zero energy here. So it creates lobes, some side lobes, and you will see in the practical experiments that the rectangular window is not a good window. What we do is normally using another alternatives, like using smoother windows, Hamming window, Kaiser window, or so many different other things. So we talked about the duality of the frequency and time domain, the ideas. We said that because the DTFT is continuous with frequency, still we're not able to take the DTFT as something inside the computer and to do the process. So we need to have a surrogate, a replacement, such a way that it's representative enough and it still has the information of the signal in the frequency domain, and you can also cope with it inside the computer. You can do the process using the computer programming. So people started to think about the same idea we had in the time domain. When we had the signal in the time domain, which was continuous in time, which was called analog, then they came up with the idea that, okay, we can take the samples in such a way that the samples are representative enough. They have the information of the signal, sufficient information of the signal, in such a way that we can easily reconstruct back the signal to its original sense if there is no process done in between. But we already saw that even that is not possible because of the quantization errors. But in any way, assuming that there is no quantization error, the process itself should be reversible. Then they say that, okay, if DTFT is continuous with time and we're not able to save it in a computer, at least we can do the same process. We can just take the advantage of what we had already in the sampling theory, and we can manage to take the samples of the DTFT, whatever name you want to put on it, but we take those samples which belong to the frequency domain representation of the signal as the samples inside the computer to work with. But the idea of sampling still should be working in that sense. For the analog sampling, we said that if signal is in time domain and you want to take the samples such that the reconstruction is possible without losing information, then the condition is that you need to have the signal which in frequency domain is band limited. And we accept this condition by default, that real signals normally they are band limited. So signal in the time domain, you want to take the samples, but you should know that this signal in the frequency domain is band limited. Then you can have a lossless representation in the frequency domain. Now you want to take the sample of a signal in the frequency domain. In the frequency domain, you want to take some samples such that the reverse process is possible. So it means that the signal in the time domain should be bounded. So signal, if it's limited in time, then you can have a lossless representation in the frequency domain by its samples. And the whole information is already inside. When the information is ready, When the signal, you have lost nothing, then it should be reversible. And you can actually do it and put it the name of DFT on it. So DFT is the reverse process. It's a kind of taking the samples from Fourier transform, DTFT. So now you can take those samples from the DTFT and you can save it in the computer. When you store the samples, you can easily work with it. You can do any process that you need. And sorry for a moment. And then we talked about the idea of endpoint sampling. So when you're doing the FFT or DFT, actually, you need to have another new parameter. And what's that new parameter? That's n. Something that represents the idea of resolution of sampling. So you take the samples from this signal, which is periodic. We know already that the DTFT is a periodic signal. The period is 2 pi. That's already we know. So the consecutive samples, they are coming with the equidistant of 2 pi over n. The more n you assign for sampling, it means the higher resolution of step you will take in the DTFT sampling. And the result is actually these coefficients, which are called DFTs. So DFT coefficients, x of k, normally they are represented by k. In the DFT domain, they say k. And the k is changing from 0 to n minus 1. N is the point of the number of samples you want to take. Is actually taking the samples of DTFT over the steps of like 2 pi over n. So k times 2 pi over n, k changing from 0 to n minus 1. And that's the result, which is called DFTs. In a simple form, graphically shown that if you want to implement it, to have the idea how it's implemented, it's actually the signal limited in time because of some reasons that I told already. So the signal assumed to be limited in time when we want to have a DFT which is reversible without losing information. What it actually means by taking the DFT is that you should continue this signal and make it periodic using the period of n, which is actually the resolution of sampling. So we make it periodic with period of n. Then, because it's continuous, it's periodic, it has Fourier series. The highest, the best representation of the periodic signals is the Fourier series. Just with few coefficients you can define it. So you can get these coefficients. We know that DFS is also periodic, but you will just need the first period, the major period of that. And those are actually the DFT coefficients of the real signal. These are the amplitudes, or better to say the magnitude. If they are absolute values, they're called magnitude. If they just if you don't care about the sign, it's called amplitude. So these two concepts are, frequently used instead of each other, but you should take care that magnitude is always positive, but amplitude should be positive or negative. Doesn't mean, the sign doesn't mean that in the amplitude. But it also has phase because it's complex. So you have both the magnitude and the phase, or the amplitude and the phase, and that's the DFT. And the mathematical form of that is shown already with this. So the DFS in one period is just the DFT. And we said that we can also represent this using matrix form, simply because it's a series. using some basis functions. We can easily use those basis functions and represent the signal. So here you see that these are the basis functions. The basis functions for the DFT, and this is the reverse. And in a closed form, you can just represent it like this. Sometimes in papers, they don't want to go through this matrix form or something, expanded. It takes a lot of place, so they just simply use it like this in papers. And the capital form normally denotes the Fourier case, yeah. And the small form is just the time domain. And also the capital, when you say the capital bolded, then it's matrix. When it's small bolded, it's vector. As an example, let's see if we have a signal x of n with these 5 samples from 0 to 4, and all are 1, like a window. So what happens if we take 5-point DFT? First of all, it means that we need to make this x of n periodic using this n equal to 5. The result of that is simply a constant 1 for everywhere. Okay? Constant 1. Now, such a thing in the Fourier series is so simple. You will just get one sample for every period. Just you have one sample, and the energy of the sample is just 5, somehow gathering the energy of the entire signal and putting everything here in the 0. Why? Because it's constant. DC is in 0 frequency. Is that right? 0 frequency with the energy of 5. Makes sense. What about the others? Well, we know that this is periodic, so we should have the same thing for every period. But what we need is just the first period. That's all. And normally it happens, the signals in the time domain, they have so verbosity, so they have a lot of coefficients which are active. But when you move into the frequency domain, they are so sparse. When I say sparse, it means that the components of the signal which are active are so sparse, 1, 2, 3, while the signal in the time domain has 500, 400, 1000. So it just takes out the frequency of the signal which has an active component. And here the active component is just a DC frequency. It's nothing. There's no change in it. Do you see any changes? I don't see any changes. The signal starts from 0, but it's constant until it finishes. So there's no change. When there's no change, it means that it's constant. So you should have something like this in the frequency of 0, which is DC. Even if you want to calculate that, there's no problem. So you start calculating n0 to 4 and put everything inside the series that we had in the 2 slides before. You come up with this expression, and you know that putting the k from 0 plus minus 5 and so on, then what you get is just 5, and for the other cases it's just 0. That's an example. Now consider if we have 10 points FFT. 10 points, the same signal, but 10-point FFT. So when you have 10-point FFT, what does it mean? It means that you're zero padding the signal. And so you're somehow introducing a kind of variation in the signal. Where is the variation? The variation from here, from 1 goes to 0. That's a variation. So it means that some other frequencies would be also activated. Okay? So you do the same process, making this continuous, periodic, and then taking the DFS, but then you see that the DFS gets some other frequencies activated. And then if you take just the first period, what you get is 4 components instead of 1. What was the reason? The reason was you're taking 10 points FFT from the signal, which is active from 0 to 4. When you did the periodicity with the period of 5, in the window that you're taking the sampling, everything is actually constant. That's why only the DC frequency is activated. But when you enlarge the window to 10, you see some more details. And those details are some other components in the frequency which are activated. That's the difference. When you put different n values, that's what happens. Let's talk about some properties of the DFT transform. Again, DFT transform is a linear transform. So all the things, all the kind of transforms we explained in the course and many other courses, they are all linear transforms. So they have the properties of the linearity. So the superposition property, you already know that. It's clear, summation of the signals and scaling them, it just happens in the output. You have the duality. If you have the signal in time domain, the DFT shows something. Then if you just take those samples in the frequency domain as samples in the time domain, you will get something quite similar to what you had in the time domain with these changes. This is a kind of representation that shows the circular rotation of the signal with the degree of rotation, which is n. As an example, if you have signal x of n, these are the samples of the signal from 0 to something, n minus 1, for example. Then that's the periodic form of the signal here, that the periodic form with n becomes like this. And then if you shift the signal with 2 samples, but inside a window of n, that's the representation of what we have written here. Shift the signals k times in the window of n. That's the meaning. Okay? So what happens if you do that with 2 samples? Then it means that the signals, these 2 signals from the beginning, they are actually going to the end. So just take this from this side and bring it from the other side. N plus 2 is shifting to the back. So you go to the back, but you don't throw it away. You just bring it back from the other side. The first one, then the second shift, the second one. So that's the window that stays after the shifting is performed. And that's the meaning. If you put it k, then that will happen for k times. That's the meaning of duality. And the circular shift of a sequence. So if you have the signal in time domain and correspondingly something in the frequency domain, in the DFT domain as x of k, then if you do the shifting in the time, shifting that happens in the time in this way, with m times. What happens to the signal in the frequency domain or the DFT domain for the coefficients? Well, amplitudes are kept preserved without changing, but the phase is changing like this. Okay? So the amplitudes do not change, but you should, because it's complex, then you should change the phase like this. These are some selected properties of DFT, but for more details you can just refer to the book where everything is written there. It's a complete chapter. Okay, let's continue the sampling A to D and D to A sampling process, because we just talked about the first process, which is A to D, but we never talked about the D to A, conversion back to the time domain. From the beginning lecture, we saw that we take the samples from the signal, but in the end, you have to bring it back to the analog form. So let's talk about the analog form and the reverse process. We already saw that for the A to D, what we have, a continuous signal goes through a continuous to discrete process with a sampling period of t. Then you get the samples in the discrete time. Then you need to quantize those samples based on the number of the bits assigned to that and the dynamic range. When you do that, you get the bits after passing through the coder. You have the bits assigned to every sample. Every sample would be denoted by a byte of data containing the information of the sample. And this is the graphical form of that. We already saw it. Now the point is that what's happening next? Well, when we have the digital signal, then we go through a process in the computer. When it finishes, we need to be back to the analog form. But let's see, if you want to study such a thing, such kind of process, we need to have a clear mind what's actually going on to the signal. How can we investigate those tasks which are performed on the signal in a mathematical form in order to follow that in analytical form, to follow that. So the input signal, which is continuous, after passing through the A to D converter, is actually changing to a discrete form signal x of n. Because here you have the analog form, if you go to the Fourier domain, that would be continuous time Fourier transform, something that you already studied in signal and system theory. CTFT, which is continuous Fourier transform. And the continuous Fourier transform, after passing through the analog to digital converter, changes to something discrete. So you need to have DTFT. Let's see how can we represent the DTFT of the signal and the Fourier transform of the signal with respect to each other. So for x of n, because it's DTFT, is periodic. We know that the CTFT is not a periodic signal. CTFT is normally represented by x as a function of j omega, not e to the power of j omega. And x of j omega is not necessarily periodic. If you have xt, continuous time domain signal, if you do the CTFT, what you get here is x of j omega, and it's not necessarily periodic. And this omega actually goes from minus infinity to infinity. Just the positive frequencies make sense, but in general it goes from minus infinity to infinity. But when you have the digitized signal x of n, or discrete time signal x of n, then when you take the Fourier, which here is DTFT, what you get is x of, as a function of, e to the power of j omega. Here the signal is periodic. Here the signal is periodic. It means that if you change omega to omega plus 2k pi, nothing changes. So, for this x of n, we have x as a function of e to the power of j omega. If you just write down the mathematical form of the series, you have xn e to the power of minus j omega. Considering the time, sampling time, that is actually happening here inside the A to D, and changing back the x of n as x of nt, what's originally is happening actually, then you can use the synthesis form of the CTFT actually. Considering that this is actually continuous in time, you can have the synthesis form of that, bring it back with this integral, which is CTFT synthesis form. And you'll get this x continuous of j omega. So that's the CTFT of a signal, time domain signal. And instead of j omega continuous time t, we just replace it with nt. So t is replaced with nt. So that's what we have. Again, these are linear transforms. And we know that the Fourier condition is absolutely summability or stability in the Bible sense. It means that both the integral arguments and the sigma arguments, whatever inside it is actually bounded. When it's bounded, even though this sigma and this integral changes from minus infinity to infinity, because we know that it's bounded, we can replace the sign, replace the operator of the sigma with integral. Change the place of that. We change the places. After changing the place and getting out of this c of j omega, because it's the sigma is actually over n, we have such kind of thing. And using the Poisson formula, we see that this is nothing but this equation. I actually had this jumping from here to here. It's not that much hard. I made it as a homework for the last semester. You can also do it as a homework. So one of the your homework is how to get from here to here. Is anybody from last semester here? You were from last semester. You had this homework. You remember that? One of the first homeworks was how to go from here to here. So do it as a homework, but it's very simple. The result is important because now we have the Fourier transform of this discrete time signal shown as a function of the continuous time Fourier transform of the signal here. And we see that this representation is periodic with this period. So you're actually making the CTFT of here periodic. And you're also scaling the frequency domain by omega over t. That's what actually happens. Periodicity and scaling of the omega. You see? That omega is scaled with this. So in actual term, it means that if your signal in the time domain, x of t in the time domain, continuous time domain, if it has a continuous time Fourier transform like this, which is active for, it's a band limited, so it's active from minus omega n. That's the omega of CTFT, not the omega for DTFT. So if it's active from minus omega n to omega n, and it looks like this, then passing through the A to D converter, what is the result? The result is nothing but, just looking at this, is nothing but, this amplitude is actually reduced to the fraction of that 1 over t, depending on what's the t here. And the bandwidth scaling is changed to omega n times t, and it has become actually periodic with the period of 2 pi. That's the result of this part. Any questions so far? So let's continue with that. Now the point is that the signal that you have in the discrete domain, it has the frequency of this omega, small omega. And we know that the highest and lowest frequency, they are from 0 to pi, and symmetrically from minus pi to 0. So it means that if you want to capture the entire signal, you need to filter out whatever inside a window of minus pi to pi. Okay? Whatever from minus pi to pi. Can you see it or not? You can see it? Even you? So, you need to have a window that takes the entire bandwidth of the signal, the possible bandwidth of a signal is from minus pi to pi and nothing else. So you take this sample, you take this window as whatever information in the frequency domain of the signal exists. And the rest of these periodic patterns actually is just because of the process is periodic, and you don't care about that. The only thing that makes sense to care about is what happens if this goes here.
Yes.
Exactly. If this maximum frequency of the signal, so if this goes here, then this also comes here. And we know that you're not able to filter. This is a filter, low pass filter. Well, it's not a low pass filter, it's all pass filter. But considering that this is a filter that just takes the one period of the signal in the frequency domain, you know that it's not implementable. So you should have some approximation of that. And that approximation actually means that part of the signal here would have some problem. So if there is kind of information of the signal around this point, you will lose that information. Okay? The entire phenomenon is called aliasing. So,
I have a question.
yes.
Regarding the limit of the DTFT, here we have omega nt, right?
Yes.
So I don't get it here in the red part, in the last part, we have xc, j omega over t. So it shouldn't be omega over t rather than omega t, the bound of my signal.
No, because the omega here, look at here. We have omega, so whatever you write here should be based on omega. Should be based on this small omega.
In CTFT, the bounds are omega capital, right?
CTFT, yes, you have this capital omega.
I'm referring to the graph.
Okay.
Okay. So in DTFT, we have omega nt.
Yes.
So what I get from the formula, it says that j omega over t. So why it shouldn't, it is not omega over t rather than omega t?
Because of x of c. We are talking about x with respect to xc. If you have the xc, then the frequency should be changed like this. So here you see that this is omega n, and omega n has this relation with omega n, the small omega n, that's omega n over t.
Yeah.
So every omega of this x of c should be omega over t.
Yeah, I get it.
Okay? As an example, you can just go through that the condition of not having aliasing is that you should have a kind of condition for the sampling. So you have t, and you know that this t is something that works here. T is the period of sampling. 1 over t is the frequency of sampling. So you're actually multiplying the bandwidth with t, which is the period of sampling. And if that period of sampling is higher than the rate, it means you will have aliasing here. In other words, if the period is higher than a rate, means if the frequency is less than a rate, you will have aliasing here. You got it? So if t is more than a rate, more than a threshold, because we have omega n times t, if t, or the period of sampling, is higher than a threshold, omega nt, getting close to this point, and it causes sampling. It causes aliasing with the consecutive patterns of the initial one. In other words, when t is exceeding a ratio, or frequency is less than a ratio. So there is a lower bound for the frequency, that if you take the samples lower than that boundary, that threshold, you will face with aliasing. Definitely you should have more than that threshold. The frequency of sampling should be more than that threshold in order to avoid aliasing. And that boundary is called Nyquist frequency. That's called the Nyquist frequency. That's explained here. So we have xc of j omega. We know that when you do, this is the continuous to discrete form so the block diagram. In block diagram format, it can be shown like this. You have the continuous time signal, and it's just like you're multiplying that with a train of impulses. Then what you get is s of t. So that's a pulse train. And what does it mean is that you have this xc as the frequency response of here in the analytic form repeated. And when it's repeated, and also the amplitude is 1 over t, so the fraction of amplitude is taken, then you need to make the change in the frequency scaling with this kind of changing. And the point is that these frequent patterns will overlap if this condition is not fulfilled. So in order to have, so here you see that this is omega nt. Here is the omega nt. And here is 0, here is 2 pi, so here should be 2 pi minus omega nt. So 2 pi minus omega nt should be definitely higher than omega nt. And the result is, in other words, if you have omega s as 2 pi over t, if you replace that, it means that omega of sampling should be at least 2 times greater than the omega of the signal, bandwidth of the signal. So the frequency of sampling, omega is 2 pi times frequency. So frequency of sampling should be at least 2 times the frequency of the signal, the maximum frequency of the signal. The maximum frequency of the signal. And that's called the Nyquist frequency, or the Nyquist condition for anti-aliasing, for avoiding the aliasing. So if you have, for example, a speech signal, which makes sense to have the frequencies from 0 to 4 kilohertz. What is the minimum frequency of sampling in order to get the signal back without any errors? 8K. 8,000 is the minimum frequency you need if you want to get the entire signal back. And even in practice, they use more. Doesn't matter if you use more or less. If you have the possibility to take more samples, you have to do that. And in computers, normally, for example, they do 16 kilohertz. Or even for the audio case, because the resolution is much important, we're talking about the audio or the music, they go to 96.1 or 98.1 kilohertz. Yes.
More energy than the higher frequency?
The highest frequency? It doesn't make sense. You're just making some extra information which is actually redundant and you don't need it. Because in many cases afterwards you're doing some processing, and one of the processes that are done is PCA. So you are doing something useless. That's a useless effort. In some cases, for example, 16 kilohertz, 2 times the Nyquist frequency makes sense, but not more than that.
After some point it gets saturated, right?
Yeah. The resolution is saturated. You don't need actually. You can get the 1 megabyte of sampling, but the result would be quite the same as 16 kilohertz. So why are you doing that? Just, you're not economically using the memory.
But you said for the musical, somebody will use 90.
Because music is different from speech. For the speech signal, the maximum frequency is 4 kilohertz, maximum. For the men is less than that. For the women is, we have some components around the 4 kilohertz. But when we talk about the audio, we mean any instruments, these musical instruments that you're using. So normally, the human ear can actually get the information up to 20 kilohertz somehow. Well, for my age, wouldn't be more than 18 kilohertz definitely. And when I get older, maybe less than 12 kilohertz. But maybe the child can actually get the information close to 20 kilohertz. 2 times of that would be 40 kilohertz. And that's why in sound cards we have 44.1 kilohertz. That's enough. And that 4.1 kilohertz is called the safeguard, or the guard band frequency. They say guard band frequency because it's a 4 kilohertz band between any consecutive patterns. But even they can go further. They go to 96 something kilohertz. Doesn't matter, but not more than that. Okay. Do you want to have a break, a short break, or we can continue?
No, I don't. So we can finish
Sooner.
quickly.
Yes.
Oh, of course. So, the D to A converter. So we had the X of n, and then we need to know what happens if we want to reconstruct the signal back to the original case. If we don't do any kind of process, would that be possible to get the signal back or not? The reconstructed signal, we name it XR of t. So this process, this filtering or process, we call it HR of t, and it's called D to A or D to C, discrete to continuous transform. Again, you have a sampling t here. So we have x of n here and here. If you write it down, XR is in the continuous time domain, so it should be written in the form of continuous time Fourier transform. And we know that in the Fourier domain, convolution goes to the multiplication. So you have the multiplication of the filter and the input. But the input goes in this time of frequency representation, e to the power of j omega t. That's the form of the convolution, but it's a weird convolution because you have n and t. But what does it mean? It means that, for example, here you can just put t as nt, or n as a sample of the time. And this convolution is in this form, actually. Now, if you want to take it back, as I showed in the previous slide, you need to put a filter here to get back if you don't do any process. The filter here should be ideal low-pass filter if you want to get it back. We saw that the gain is 1 over t. So in order to be back, you need to have a gain of t. So that's the gain of t for those components which we need to be given a gain. We have to make a gain of t. The frequency range would be pi over t, the same way that from the continuous to the discrete, we actually made omega over t. Now we have to bring it back, actually, pi over t. And for the rest, it's 0. Representation of this in the time domain is something like that. In the frequency domain is something like that. The graphical form is something like that. So omega c and minus omega c are the cutoff frequencies. That's the gain. But this one in the time domain is a sinc function. That's the sinc function. That's the mathematical form for this sinc function. and the zeros of the sinc happen in t period. These are multiplications of t. So this sinc function, we know that every sinc function goes from minus infinity to plus infinity. Is that possible to have this convolution in time for the signal with something that goes from minus infinity to plus infinity, and then you're shifting that sinc function again and again and again, and you need to go back to the continuous time signal? Of course it's not possible. What really happens is that this sinc function is actually frequently summed up with this shifted version of itself. So for every sample, you have one sinc function that is actually placed on that sample, and then it's summed up with the shifted versions of the previous samples. And this is the graphical representation of that. So you have the sinc function at t0 and t, and they are actually summed up together. So it means that in general, reconstruction, the complete reconstruction is not possible. The complete reconstruction is not possible, and definitely you will have a kind of error here. There was an error in the beginning, quantization error, and there is an error in the end because of the sinc error, sinc function error. So these two types of errors are unavoidable in every A to D and D to A conversion. There's no choice. You have these two errors. And these two errors reduce the amount of gain, SNR gain, that you should have, the bound limit, so the upper bound of the SNR gain that you can get from any DSP process in practice. So here you're just having interpolations or superpositions of sinc functions for every sample to get it back in time domain. There is one thing that we can do in order to a little improve that error that might happen. And even if it's so weird, but we do it in practice. So we see that if the signal is really high bandwidth, the frequency, the highest frequency of the signal exceeds over pi over t, which this is actually the frequency of sampling, the highest frequency sampling. So if the signal has more frequency components than what we can sample, which is here, and the symmetric form here, what we do is we put a filter in the beginning to cut the information of the signal, whatever is more than that possible sampling frequency. We cut it down. Even if it has some information, we ignore it. It's much better to ignore that information in the beginning than leave it with the signal until in the end to face with it again. Because if you do that in the beginning, you will just get this part of the information lost. But if you forget about that filtering here, then in the process, which it becomes periodic, you have the coming patterns from the other sides, and it actually goes through the other side of the information. And it screws up even more information of the signal in the frequency domain. You can investigate this, which is called anti-aliasing filter. Anti-aliasing filter, before starting any process, is done, before even going inside the continuous to discrete conversion, A to D conversion. And that implicitly means this anti-aliasing filter is actually applied to the continuous time domain signal, not the discrete time domain signal. When there is a filter and it's supposed to be applied to the continuous time domain signal, it means that filter should be implemented in analog form, not the digital, using the capacitor, inductance, and resistors, and so on. So everywhere when you hear about anti-aliasing filter, it's an analog filter. If any analog filter vanishes by lapse of time, there is one filter still remained. and that's the anti-aliasing filter. So you got the idea, I think. You cut the frequency from here, because still there is no repetition of this pattern. You cut the frequency from here, you will just get this part of the information, the frequency lost, but it's much better, because even in that case, if it's becoming periodic, then the consecutive periods of that signal will not go inside the signal, the main pattern of the signal, and will not screw up anything more. But if you don't do that, then the overlapping patterns from the other periodic processes will go inside the signal and try to screw up even more frequencies. So something like that. It comes from here to here. That's the anti-aliasing filter. In general, for every A to D and D to A converter, which in mathematical form is represented like this, you have all these small components. So you have the anti-aliasing filter, which is in time domain. That's why it's represented by J of omega, capital omega. Then you have sample and hold, and then you have digitization or quantization of the signal. You do the process, then you do the reverse process, and here again the compensation filter, which is trying to make this signal back, is in the time domain. That's the entire process, and you have two types of errors happening here and here. And you know that if the signal has a high bandwidth, then cutting the frequency from pi over t is using the analog filters, analog anti-aliasing filter, is actually impossible. So designing an analog filter in that bandwidth is really a hard task to do. There is a mathematics, a part of mathematics that actually helps to implement this idea in a more relaxed form. So it actually relieves you from designing a very harsh anti-aliasing filter to the cost of some more computational effort in the coming blocks, building blocks inside the A to D converter. And that's called oversampling. There are many papers belonging to the 80 and 90 decade. They were talking about oversampling A to D converters, sigma delta converters, and so on. Even today, you can find some papers from the electrical engineering researchers that they are trying to make the samplers more sophisticated. So the idea of oversampling comes from this idea that this motivation, that this anti-aliasing filter implementation of that is really hard. What they do is that they try to just design something more relaxed, but what they do is they take the oversampling here, but they need to have anti-aliasing filter here with something that's in digital form. It can be implemented, there's no problem. And then they do the downsampling, and the upsampling and downsampling is the story of what I'm going to explain in the next slides. It's just for your experimental knowledge, but I will go through the down and upsampling and changing the rate of sampling. What I said about the anti-aliasing filter is actually more graphically shown here. You have the signal in the time domain, and the bandwidth of the signal is normally from omega n to a symmetric form of that, but there are also noise in it. So the noise actually occupies the higher bandwidth of the signal until the maximum possible frequency of the signal. The point is that you can actually take the anti-aliasing filter here not to be so sharp. The sharper this anti-aliasing filter, it means that the larger amount of elements you have to use in the analog form, and the larger amount of, the more elements, the capacitors and inductance that you use, it means that non-stability is increased, adding zeros and poles, and then the system becomes more non-stable. So they say that, okay, let's have an anti-aliasing filter which is more relaxed. So that changes the shape of the noise in the frequency domain like this. And then when you have in the digital domain, when you have the periodicity of this pattern, what happens is that the consecutive patterns from the repetition of the original pattern, they overlap each other, and that part which is actually cancelled is the noise part because of the noise shaping. That's the idea of oversampling as and noise shaping in more sophisticated A to D samplers. In the end, what you will get is that you have the signal, if assuming that everything, the signal has used the entire bandwidth. So you have the signal and the repetitions of the signal happening like this. So no more overlapping. But we know that it's in the ideal case. Now the idea of changing the sample rate. That's really necessary in the practical experiments to have the ability to change the sampling rates. For example, someone gives you a database, and that database contains a signal which is already sampled by 44.1 kilohertz. And the entire process that you're doing actually is with 16 kilohertz. And you want to know what happens when everything is in 16 kilohertz. Or at least you have some training data or the test data, whatever, which is in 16 kilohertz. You have to do everything in a controlled area and in a unique area, so the conditions of the testing and training should be the same. And it's not good to have some sampling rate in the training case and something different in the testing case. So you want to know everything in the 16 kilohertz, but you don't have any access to those people that have already created those databases. So what you should do? Do you want to look for those people to make them sit back again in their desks and to talk about those stories, for example, in the Wall Street Journal, and to gather the data again? But in this time with 16 kilohertz, it's impossible. You cannot find them. And maybe the database belongs to 20 years ago and those people are already passed away. So the DSP engineers, they do not just stand aloof. What they do is that they actually change the sampling rate mathematically. There are two ideas helping for changing the sampling rate: upsampling and downsampling. Downsampling means from the samples of the data, you're ignoring some samples based on some condition, some regulation. For example, you have this signal x of n happening like this, starting from 0. Assuming that the real values are also possible. If this is the signal that you have, and you do the downsampling. What downsampling means here? For example, you do the downsampling with the range of 2, which is actually shown by x2 of n. It means that taking the initial sample to be preserved, then every other sample should be cancelled from the next one. So this one, you ignore it. This one, you take it, but you put it back here. So the next sample right afterwards is this one. Then you ignore this sample. You take this one. But look at the timing sequence. the timing sequence. It's not that you put 0 in between, but you ignore that and you shift this to the back and you create a new signal out of that. Then you ignore this and you put this one. And so on and so forth. So this one, you ignore, you put this one, you ignore this, then you put this one. And if it continues, then we can have such a thing. Here by downsampling, what happens? Yes, please.
Can you also take the average and
Here, downsampling is somehow the averaging.
no, but we're just ignoring the
We are ignoring, you know, because the downsampling rate is 2, what we are doing is actually every other sample after the first sample should be cancelled. So we are ignoring this one, this one, this one, this one, and so on and so forth. If it was 3, then we keep this one, these 2 are ignored, we keep this one, these 2 ignored, we keep this one, and so on.
yeah, I get this, but my question is that generally, like I have read about downsampling is that if you suppose have even number of elements, then you just average the first 2 and then you get the next sequence.
What it actually happens in mathematical form, it's just the representation of how downsampling in practice you see it. But then we go to the mathematics, then we go to the Fourier transform, what happens. So we have to go through every concept from different aspects. So different views of that. So what really happens in every of those views, we will see next. It's just in this slide. But in case of what downsampling means in practice, what downsampling means, that's the meaning of downsampling. But here, it comes up with the idea that you see, for example, these changes here, they are ignored. So it means that here you have a very high frequency changing. From positive to negative, it's very high frequency changing, but then you ignore that. You ignore that. Again here, you ignore this. For this type of signal, it's somehow like you're smoothing the signal. But it doesn't necessarily mean everywhere it's like that. Yes?
So if these negative peaks weren't maybe noise, we would lose information because we downsample.
Exactly, but these are all in the slides. Just wait for a moment. In 5 minutes later, we'll have the solution, the answer for all of your questions. So that's the meaning of downsampling, that's all. And when you say upsampling, it means that, for example, if you had upsampling with the range of 2, it means that between any 2 samples, add 1 0. So you add 1 0 in between. That's all. So upsampling by the range of 2 means you have, for example, 0. Then you add 0 here. Then the next one is 2. Then another 0. Then you have 1, and so on. That's the upsampling with the range of 2, with the rate of 2. You add 1 0. But they all have their own meaning. It's not just a useless effort we do. We need this up and down sampling, specifically in the filter banks. Yes?
As we are in downsampling, we are losing some information. Is it not better to somehow put the average value of 2 values in upsampling rather than putting 0? That's some kind of
Some of the
interpretation.
concepts, yes, but just it's a kind of note. Some of the concepts individually by themselves they have no meaning. It looks so crazy. Why we should do downsampling and losing some information? Or why, if we can represent a signal like this, why should we add some zeros in between? But you get the concept, but when you have some practical experiment, then you see that using this up and down sampling, you can reduce the amount of computational effort in the filter bank in a large scale. So up and down sampling by themselves, they might have no meaning. They just look so crazy. But in practice, using the subband coding and filter banks, you see that using up and down sampling, they help you to have a highly efficient computationally implementation of the filter banks. So it means that from the n square order of magnitude, it becomes n log n. Instead of doing 1 million multiplications in a time, you just do 10,000. That's enough. So 2 order of magnitudes is less, and it's a lot of meaning for us. 100 times faster. And that's just because of using the concepts, which individually, if you just look at the concept by itself, it has no meaning. So I brought up the idea of down and up sampling, and it has some advantages and disadvantages. It has some problems. We will face with the problems. Whatever process we take, we have to know the effect of that process in the entire system. We need to know what actually happens when we do the up and down sampling, but then we explain in the slides where actually is the practicing form of this up and down sampling in the filter banks or the subband coding. So, definition of the downsampling. Normally for the downsampling, as you said, it brings up the it's something that boils down to loss of information. And what really happens is that we need to have a filter at the beginning. That's the decimation filter, or the entire process is called decimation, which means low pass filtering plus downsampling. The entire system is called decimation. I will come back to this after I explain everything graphically, which is more representative. So let's talk about what happens if we do downsampling. This is the signal that you have in time domain. You have the signal in the frequency domain, which is periodic, like this, x of e to the power of j omega. If you do the downsampling with a range of m, here as an example, m equals to 2, the thing that happens is that you're actually reducing the gain of these frequency responses to 1 over m. M is 2 here. But what else happens is that this bandwidth is actually extended 2 times or m times, depending on the m rate of downsampling. So here you see that the frequency spectrum is actually getting wider. And it has the danger of overlapping with the consecutive patterns of the other periods. So downsampling, if m is not chosen wisely, the result of that would be overlapping of the consecutive patterns and aliasing. So if we take the downsampling, if we have such kind of thing, we need to know already that m should be sufficient. You cannot just wildly take the m, something really large, because it definitely creates some kind of overlapping and you will lose information. So the point is that what happens for the downsampling is like that, but again, to avoid this kind of overlapping of the frequency patterns, what you can do is the same as anti-aliasing filter. You can just use the low-pass filter in the beginning. That's why in the downsampler, they use a low-pass filter in the beginning. And that low-pass filter cuts off the frequency pattern in pi over m, because we know that if we do the downsampling, that pi over m is expanded by the scale of m. So it means that it will reach to the point of pi, which is the highest frequency. You got it? That's the reason of using this low-pass filter in the beginning and then doing the downsampling. The entire system is called decimation. And that's the mathematical form of the downsampling. For the times d or m, for example, it's nm, here 2n is the downsampling with the rate of 2. And what happens So the frequency, you can just go through the mathematics based on whatever we already know that. But the definition is like that. So you have the gain, which is reduced by the amount of m, and also the pattern, the frequency, which is actually expanded by omega over m. When you say omega over m, it means that your bandwidth is expanded m times. And that was the graphical form of that. If overlapping happens, then you will lose the information. That's why you have to cut off the frequency from somewhere, such that you lose less information as possible. What is upsampling is the other way. So this adding the zeros here, or zero padding. They say zero padding. The form of zero padding is like this: n over L. L upsampling rate. So when you have upsampling by the rate of L, you need to add L minus 1 zeros between every two samples. Here you have 2 by the rate of 2. It means that we need to have 2 minus 1 means 1 0 between every two samples. In general, L minus 1 zeros between every two samples. What is clear is that it's not dangerous for the spectrum, because the spectrum is more contracted, so that's not dangerous in case of the aliasing. So the spectrum will be more compact, and therefore mathematically you don't need any filter in the end, but practically you use a kind of filter. And that is only because that's as a system. It might happen in some places that you use the down and up sampling, in a cascade form, and when they are cascaded, then you need to have a kind of filter which has the conditions of the filter here and the filter of the decimation. So even though mathematically you don't need, there is no intuition behind having a filter afterwards, if you just look at the interpolator or something is called upsampling or interpolation system. But in practice, you need to have a filter again, low pass filter, with the cutoff frequency of pi over L. We just take it. So that's for upsampling. The result of that would be nothing but pressing the spectrum. It's not dangerous by itself. But then you can have changing of the sampling rate by some non-integer values. For example, you say that change the sampling rate from 16 to 80 kilohertz. Then you have to figure out what kind of fraction you need to use, the numerator and denominator of the fraction. And then based on that, you can have the interpolator and the decimator. Which one should be the first, decimator or interpolator in that sense? If you use decimator in the beginning, that's the danger of losing the information. So it's better to have the interpolator in the beginning than to have the decimator coming in the cascade form. So when you have the non-integer form of changing the rates, it's better to have the cascaded form of the decimator and interpolator, with interpolating coming first. And then because you have two low pass filters here, you can ignore that, two low pass filters. You can just make up some low pass filter which can fulfill both the conditions that we have here and here. So you get the minimum of the cutoff frequencies that you have here. If that minimum is by pi over L, we take that one. Otherwise, we take the other one. Something that brings up the similar condition for both cases. Use that frequency as the cutoff frequency, and then you design the low pass filter between the up and down sampler. So using this structure, you can change the sampling frequency of any signal to any range that you like. Of course, if you want to, for example, reconstruct a signal which has already been, for example, sampled by 8 kilohertz to something more than 8, then you will lose some resolution because the original signal is not more than 8 kilohertz. So it's not magic that you will get some more information suddenly appear somewhere. No. But you will have a sense of interpolating the signal. If it, yes.
So that's what when you actually do upsampling, you would interpolate the data in between, right? You just
That's just an interpolation. That's all. And the interpolation is actually done using the sinc function. So that's a difference between the linear interpolator and the upsampling interpolator. The linear interpolator is actually just putting, for example, if you have here one sample and one sample here, when you see somebody says that we need a linear interpolator. Linear interpolator in this sense means there is one sample in between, and that's just putting a value here. When there is a line passing through these two nodes, these two values, then the linear interpolator is nothing but putting something here on the line. That's the linear interpolation. But here it's not a linear interpolation. It's a sinc-based interpolation. We can investigate through how it's different with the linear interpolator, but practically this type of interpolation gives more information to the signal and makes more sense than just using the linear interpolation. So, here it means that you're actually reconstructing the signal with the interpolation, which is sinc function, and shifting of those sinc functions actually. So we know about the down and up sampling, what it theoretically means, but about the application, when we go to the filter bank, design of the filter bank, and polyphase filters, then we will explain how the polyphase filters are implemented using the up and down sampling, and computationally much more efficient than the standard version of that. So we have the DFT algorithm. I don't want to take your time to go through the FFT algorithm. Just I want to give you the flavor of how people came up with a fast implementation. Because you know that FFT algorithm really somehow, of course, was a kind of magic for the engineers. People were trying to implement DFT everywhere, but they had the problem of the computational cost. So when first engineers, the researchers came up with the idea of fast Fourier transform, that was a kind of revolution in the DSP or the engineering. And that's why FFT algorithm, there were 10 algorithms selected by the community of scientists as the most privileged algorithms of the millennium, or I don't know, maybe the 20th century, and FFT was among those 10 that made a lot of progress in the signal processing applications, from radar and so many other things. So FFT, just to know what they actually did, is they just used the idea of periodicity of the eigenfunctions. So this Wn as the eigenfunctions, if you just look at these eigenfunctions more carefully, you see that they can be divided into two different sequences, one of them to be even and the other one to be odd. So if you just replace or just permute the samples of the analog signal in such a way that every odd sample to be in one set and even samples in another set, and then restructure everything to implement the DFT, then you will come up with the idea of radix 2 FFT implementation. So you have the definition for the DFT, but the only thing that differs is that you take the odd and even, the even and odd samples. The sigma is broken down into two sigmas, one over the even samples, one over the odd samples, and their consecutive, respective eigenfunctions, those eigenfunctions which belong to the sample. And if you use such a thing, then you can simplify that, because we know that, for example, this function omega sub n to the power of 2nk, it can be, it's actually like this, and it can be rewritten in this form or in this form, and for the other part it can be rewritten in this form, and this is something common in both cases. It's common in both cases. So why should we try to calculate something 2 times? We can ignore that. And that can happen for every other step in layers. So just trying this, putting back inside the original formulation, we got this. YK, ZK, and so on. So for the endpoint DFT, the original version of the formula, we made it as 2 n half point DFTs like this with this formula. And the idea was the symmetry and the periodicity of these eigenfunctions. That was the only reason we could do that, breaking down the formula into 2 parts. In the implementation stuff, what they actually did is, if I take, for example, the even values and the odd values, so it's somehow reordering the input values of x of n. So you take the sample of x of n, but instead of just giving the order, that's the samples in order, you're just making this order, but in this way. And then you can give it to n over 2 point DFTs. And this can happen in different layers, multi-layers. So the next step would be n over 4, and then continuously, until the last step, which is just a 2 point FFT, DFT actually. Implementation of the DFT in this form, even though the original one had the order of n squared, I mentioned here that the original one, DFT, is actually n times n complex values, that will reduce to n log n value, n log n order of computation. So you see that we take this, we take the other one for the next sample, and just by doing that, you can create actually a very nice representation of the DFT using different steps, different layers of radix 2. So radix 2 means division by 2. Some layers, division by 2, in such a way that the final scale is coming back to the same DFT, but it's much, much faster. The original DFT is n squared. If n is, for example, 1000, normally we have for speech n 1024. So assuming it's 1000, then DFT of 1000 sample is 1 million samples. But in case of FFT, it's just 10,000. With 10,000, you can get the same result. Completely the same result, much faster, 100 times faster. And that was a revolution. Even they developed that with different types of FFTs, and now we have, a dozen algorithms to implement the FFTs, and some of them are already in MATLAB. In MATLAB, if you want to take the DFT, just write down FFT. For 1-dimensional data, FFT works. For 2-dimensional data, FFT2. For example, you have image, and you want to take the 2-dimensional FFT for the image, you write down FFT2, that's all, and it's implemented. Okay, we have run out of the time, but I wanted to implement some MATLAB examples. Maybe if I can find a chance for tomorrow, I will do some MATLAB examples in the class. Otherwise, I'll try to just put some samples for the MATLAB to upload that in the website. You can take it. of course, there are so many MATLAB examples in internet. Just by Googling, you can find it. But in order to just have a more coordinate form of the class and the MATLAB examples, I can try for that. Any questions you have? Yes.
With regards to the registration, we didn't get any name or something like that, so how do we know it's done?
I actually don't know about the registration and the process that you need to take for that, because I've never registered in the website for the course. So you can ask the friends if any questions you have. If already somebody knows about how to do the registration.
I mean, like, there's a portal, we did it, but then after that, no verification.
There were no acknowledged, huh?
Yeah.
The system will not send me
Really? Confirmation email. You can drop an email to Professor Clarko and to ask for it if you should get any acknowledge, or I don't know if has already been done.
No, I mean,
Because-
you can send a general email to the group for the
I don't
the
have
mailing list.
no. I don't have any mailing list for the students, so I don't know how many students and what are the names. I have no idea.
Okay, for
I just
mailing
make the website and fill it with the information. That's all I do.
Basically, the system of quality department doesn't send information letter, confirmation email to the student, but normally the courses are offered by Professor Clarko. Each course has a
Mailing
some
list.
kind of mailing list.
So maybe one of you can ask Professor Clarko whether the names are already in the list, and then
I will do it.
you will do that.
Yeah, I will contact Professor.
So just write it down that please send the copy of that to me, because I don't have the names, so it will be nice. Well, definitely I will know that based on your homeworks, but it's better to have officially the things. Thank you.